Quick overview of what we're going to talk about. We're going to talk about open loop control, which is really not control at all. Closed loop control, or where feedback is used to control the process. We're going to talk about how PID control works and discuss the PID control equation and how it works. Open loop control is basically just set it and forget it. Imagine you're going down the highway and you notice that when you have the gas pedal at a particular position, your car goes at the speed you want, and so you stop paying attention. You just hold your foot at that position so the pedal remains at that position, the accelerator is at that position, and you're going, say, 60 miles an hour. Everything's wonderful and life is good. Now, you and I know that that won't last very long. You know that you can't just set the gas pedal and your car maintains 60 miles an hour, or any speed for that matter. Of course, the reason is because disturbances comes along. There are things that come along that mean you're going to need a different amount of effort, if you will, in other words, accelerator position, in order to maintain 60 miles per hour. So what happens, of course, with open loop control is, say you start climbing a hill all of a sudden, and now that pedal position that you thought was perfect for 60 miles an hour generates 40 miles an hour, right? Because now there's something that has come along that has changed the process. There's more effort required in order to maintain 60 miles an hour. And so we've got a graph here that shows over time what happens to your speed. You were going along just fine at 60 miles per hour. All of a sudden you encounter this slope and your speed drops down to some new stable position of, say, 40 miles an hour or so. So open loop control does not work. You can't set things and forget them and just leave them alone. And this is true of many things. Now, to show you what we're going to do, I'm going to start off creating a block diagram, and we're going to add pieces to it as we go. So far, the only thing we've discovered is that we've got a control variable, something that we can manipulate, that affects a process, in this case our car, so that the process variable, or the thing we actually care about controlling, can be changed. Now, there's a lot of terms I'll use here, and there's a lot of interesting analogies you can make in real life. I might make a few myself. But if you think about it, most things that you want to actually control, you can't. You cannot directly control most things that you really wish you could. For example, you can't control exactly how much money you make. Okay? Now, you can go to college, as you are doing now, and try to increase your value so that you can earn more money. That's certainly a possibility. But you can't just say, I'm going to make $100 an hour, or whatever it is that you want to make. You can't do that. There are many things that we'd like to control but can't. For example, you can't control the position of your car on the road. You might think you can, but what you actually have control over is the steering wheel. And as you turn the steering wheel, that adjusts the position of the car on the road, assuming that the process works properly, right? Part of the process is the steering linkage and the rack and pinion and the tires on your car and the idea that you even have wheels on the front end in the first place. All these things affect whether or not the manipulated variable, or the control variable, your steering wheel, actually affects the process variable, which is the position of the car on the road, that you want to affect. So often in mechanical systems, in life, and all sorts of things, we can't actually control the process variable, or the thing we need control over. Rather, we manipulate a control variable. In this case, to control our speed, we can't actually control the speed of the car, but we can adjust the pedal position. Now, of course, if the linkage is broken in the pedal position, then it's not going to do anything. So we've got to somehow figure out how to use this control variable to adjust the process so that the process variable remains where we like it. Now, of course, we're assuming that the process will work, that there's a valid linkage between the accelerator and the engine in order to adjust the engine's power output. So we're assuming the process works. It's just the point is you can't just set the control variable at one value, in other words, one pedal position, and expect the process to do exactly what you want. That's not the way things work. Because there's always disturbance that comes into the process. There's always things that affect the process besides the control variable. And the goal of a controller is to adjust the control variable to compensate for those disturbances and thereby maintain the process variable at some desired level. Now, if we're going to control something, we've got to measure it, and this is where the term feedback comes into play, because what we're doing is feeding back a signal from the output of the process in order to manipulate the input to the process, the control variable. So without measuring things, you can't control them, and that's another nugget of truth that comes up in quality control and many other places, but for our purposes, what that means is that if we don't measure the speed of the car, there's no way we can control it. We have to have some measure of what we want to control before we can attempt to control it. So the things that I'm adding here to the diagram for this slide is the feedback path, the measurement of the car's speed, say in miles per hour. Now, in order to adjust the pedal position, we've got to know what the target is, right? You can't aim something without knowing where the target is, and in this case we can't aim the speed where we want it if we don't know where we want it. So maybe you want the speed limit, 55 miles per hour, and you're doing 60. Well, then there's some error, some difference between the process variable, in other words your speed, and what you desire for it to be. So error is the difference between what you want and what you've got. It's always the set point, in other words what you're shooting for, the target, minus the process variable, in other words minus the amount you currently have, in our case our current speed. Now we can dial in the set point. That's up to us as the user to decide what the set point should be, but ultimately we'll have a controller that will hopefully take what we want, the set point, compare it to what we have, the process variable, the speed of the car in this case, take the difference between the two mathematically, simply subtract the set point or the process variable from the set point, and that difference is called the error. Now the job of the controller is to take the error in on one side and on the outside decide how to change the control variable. It doesn't really decide most of the time on the actual setting of the control variable. Normally the control variable, in other words the pedal position, starts at some particular setting, and then the controller adjusts from there. And this is true of your cruise control. Really, the cruise control in your car is likely a simple PID controller, and what it really does is you're going along, you set the cruise control, you turn it on, and what it does is it notices where the pedal is at that moment in time, assuming that this is the pedal position that gives you the speed you want, and all the cruise control does is adjust the accelerator pedal from that point. So the job of the controller is to take in error and somehow from that error decide how much to manipulate the pedal position in the context of a cruise control system. And in any system, it doesn't really matter what it is. If you're trying to control the temperature of a furnace, say a gas-fired furnace, you're going to need to know the difference in air. Probably temperature is what you're trying to control, so the difference between what you want the temperature to be and what it actually is, that would be the error, and then from that you have to somehow have the controller compute the change in, say, the gas flow rate to the burners in order to adjust the temperature in the furnace. Now we've almost got our whole system set up. You'll notice that I've attached the controller in where the error signal can now go into the controller, and now the controller, however it works, is deciding how much to change the gas pedal position. We're almost there, but we're really not quite to the actual pedal position yet. We have to add one more thing. We have to add that open loop pedal position bias that I mentioned earlier. Just like when you start your cruise control and you have the pedal depressed so that you're maintaining the speed you desire, that's the open loop position. That's the position from which the pedal has to be changed or manipulated in order to reject disturbances that might affect the car, which is our process, such as road slope. The slope of the road might change, and that might affect our car, meaning that we have to somehow change the pedal position. Obviously, if the slope increases, our speed is going to start to drop. If the speed starts to drop, then our desired speed minus our current speed will be a positive error. That positive error needs to go into the controller, and somehow the controller needs to understand that that positive error means that we need to change the position of the pedal deeper, right? It has to be pressed harder so that the speed of the car can come up to the desired set point. But we have to always adjust the pedal from this open loop pedal position, this bias position. Now, how might we do it? How might the controller use error in order to decide how much to change the gas pedal? How would you do it? Well, if error is positive, well, then we need to increase the gas pedal. So that seems pretty straightforward. Why don't we just make the gas pedal increase when error goes up, right? If error is a positive thing, just increase the gas pedal, maybe proportional to the amount of error, because the bigger the error, the bigger the difference is between where our speed is and what we want, and the bigger that is, the more effort it's going to take. So let's add in a proportionality constant. We'll call it K sub P. And so for this controller to decide how much to change the control variable, it's just a simple math equation. It's whatever gain we decide, the proportional gain, Kp, multiplied by however big the error is. And notice all we're really doing is changing the gas pedal position based on the magnitude of error, how much error there is, how big the error is right now in the moment. You got to understand that we don't just compute the difference between set point and error, or set point and process variable once. This is something that's running continuously. It's constantly monitoring the speed, and the controller is constantly modulating, is the word for it, moving the pedal around so that we hopefully can hit our set point with our car. In other words, hit the speed we want. So what we might have is, you say we're going along 60 miles an hour, we turn our cruise control on, and we've got a PID controller, well, a proportional only controller. That's what this part is a proportional control, where the effort is proportional to the error. We've got this proportional controller, and all of a sudden we notice, hey, there's some error. The error is non-zero. That multiplied by the gain. We'll talk later how we figure out the gains, but just pretend it's 1 for now, okay? The error multiplied by the gain calculates the change in the gas pedal. So the gas pedal gets pushed down a little farther. And what we would notice is that our speed would not drop to the 40 miles an hour we saw before, because the pedal didn't remain constant. If this controller is active, when there's some error, the controller is going to push the pedal down farther. That's going to make our engine give more effort, which means we'll be climbing that disturbance, that hill, at a higher rate. And so our speed won't drop down all the way to 40 miles an hour. Say it drops down to 45 or so. It's better than it was, but it's still not the 60 miles an hour we wanted to maintain. And so you see our error in the green line down there. The error goes from 0 up to about 15 miles an hour because our speed on the blue line has dropped from 60 down to 45 miles an hour or so. The numbers don't matter. The point is that it's better, right? We're not to where we wanted to be. We're not at 60 miles an hour, but it's not 40 miles an hour like it was before. So this controller is successfully rejecting some of the disturbance, and that's its job. Now, it's not very good. So how could we improve it? Well, remember that proportionality that I mentioned before, that case of p-value? What if we just make it bigger? If we make it bigger, what will happen is the same amount of error will generate more change in the gas pedal position. It'll push the gas pedal farther if we make K sub p bigger. So if we make K sub p bigger, maybe we get to 52, 53 miles an hour with only 7 or 8 miles per hour of error. So that's better, but it's still not the 60 miles an hour that we wanted. And so what you might notice is that this proportional only effort will never actually get us to where we want to be. And the problem is that, see, for us to change, or for the controller to change the gas pedal from its bias position to somewhere deeper so that our engine will put out more power, we have to have some error. Because think about it, if we were at 60 miles an hour, which is where we want to be, then the error is exactly 0. And this proportional only controller will multiply any proportional constant, doesn't matter, by the error, which is 0, and it'll say, oh, the pedal can go back to its bias position, right? And if we're still climbing a hill, that means we're doing 40 miles an hour. Of course, that's not what really happens. It settles out to some intermediate balance value where there's just enough error to keep the pedal in just a deep enough position so that we maintain some steady state. Another thing that can happen if you increase the proportional gain too much is it'll make the pedal, in our analogy, slam all the way down. That'll make the engine go too high power output, which will make us go too fast. And then with too high proportional gain, then the pedal, once we're going too fast, will go all the way back to nothing and try to get the engine to output 0 power, which means that we'll go too slow. And so we'll have this constant oscillation. And really that's on-off control, but we'll talk about that a little bit later. So what's the solution to this problem of non-zero steady state error? Notice that's what's happened, right? If our proportional gain is high enough to be useful, well, it might be so high that we get oscillation. That's not good control. But we can never eliminate the steady state offset, the error at steady state. We can never get the gain high enough because it starts to oscillate. So the proportional only controller suffers from non-zero steady state error. That's the problem with proportional control. How do we eliminate that? Well, we add another term. We add something called integral control. And integral control just increases the control equation so that we're not just looking at the error itself, but now we're looking at the error over time. Now don't be thrown off by this integral term here. Integration just means adding up. I'll give you a quick analogy that'll hopefully help this make sense to you. Have you ever had a friend who kept track of all of your past mistakes, all of your insults and your injuries to them? And not the kind of friend you really want, right? This is the kind of person that remembers 10 years ago when you didn't see them in the store and you went past them, right? And is still offended by it. Well, integral is kind of like that. What the integration term does is it simply remembers error. It adds it up. That's the way it remembers it. It doesn't remember exactly where the error came from, and that doesn't really matter. All it does is just kind of take, okay, what's the error right now? Throw that on top of a pile, okay? And when we come back through the loop, and we calculate again, how much error is that? Multiply by the amount of time since the last time we checked, add that to the pile. That's all we're really doing. And so if you look at the graph here, what you'll notice is that the integral term is represented by the shaded green area under the error curve. All that the integral term does is add up area underneath the error term, or under the error curve. And notice that that area gets bigger and bigger as long as error hangs around at a non-zero amount. The nice thing about this is that if we've increased our proportional term just as much as we feel comfortable, and yet we still have non-zero steady state error, in other words, our process variable is not at the set point because proportional control can't completely reject disturbances, then what will happen with the integral term is it'll start adding up the error and it will start asking to change the control variable, because look, it's an addition term, right? We've got the proportional term still, now we have an integral term, and those two together, in other words the sum of the two, decide how much to push the gas pedal. So what will happen as time goes on is the integral term will be the one saying, no, let's change the gas pedal more, let's push it farther, let's push it farther. It's adding to the change in the gas pedal position, the change in the control variable. So what ends up happening with this is actually really nice. In reality, this is more what it looks like. You'll notice that the speed, the process variable, the blue curve, drops down and then recovers. The error term goes up. We get some non-zero error, but it eventually goes down to zero. That's because the area beneath the error curve exactly compensates for the disturbance. It compensates for the road slope. Now, of course, in the real world, the road slope changes, right? It goes all over the place. And so error could be positive for a while and then negative as we start going down the other side of the hill. As a matter of fact, that can be the problem with integral control, is something called integral windup. Because what can happen, say that we've got this beautiful car, we've just graduated with our engineering degree, we're going to go on vacation because we're happy and we've got our job. Say it's in Florida. Let's make this a very rosy scenario. And if you're like me, what you really care about is the efficiency of the car, not so much the sportiness. I know I'm getting old, but that's what I care about. I care about miles per gallon because I get sick and tired of paying for fuel. So let's say that we bought this car, and being the wise engineer that we are, we've opted for the 4-cylinder engine. I know, it's sacrilegious, but just go with me on this one, okay? So 4-cylinder engine in our, I guess that's a Camaro, okay? So it's fuel efficient, but we're going from Indiana down to Florida, and we got to go through the Smoky Mountains, and guess what happens? Well, there's hills to climb, there's valleys to go down through. The valleys are fun, but the hills are hard to climb because we opted for the little 4-cylinder, right? And it can't really go at full speed and carry this heavy car up a hill at full speed. And so what might happen is, you know, we start to climb a very steep incline, and so we want 60 miles an hour, but the car drops down to less than that, and the pedal's to the metal, right? The controller has integrated over time, and it's added up all of this error, and it's decided, hey, the pedal has to be all the way down, but the car is simply not capable of climbing the current hill at 60 miles an hour. It's saturated. This is controller saturation because the control variable is at a limit. It's at the positive limit. Now it could be at the negative limit too. Both the positive and negative, or the zero limit, are valid limits. But in our case, we're trying to climb and we just can't. We can't maintain 60 miles an hour because this engine with this car simply cannot do it. What's going to happen is, see all that area beneath the error curve? That's going to be added up. And as it's added up, the controller is not going to forget that. It's going to be a number in memory somewhere. And quite frankly, it's just going to keep adding to that number as we keep trying to climb this hill. And what do you think happens when we crest the hill? Here's the fun part. When you crest the hill, there's all this area, this positive area beneath the error curve. You notice, if you can see the graph in the green line there, it's from time 0 to about time 2.5 seconds. Okay, that amount of area is still a number in the controller. And as far as the controller is concerned, it is a number that means the pedal needs to be pushed as hard as it can, because it's that second term, it's that integral term. The integral term is huge. And so that means that the control variable, the gas pedal position, is in saturation. It's all the way down. And so as we're now crested the hill and we're going down the other side, the controller remembers all of that error, and now instead of doing 60, it wants us to do 80 miles an hour instead. Okay, so we're going downhill. This is scary. We're doing 80 miles an hour, and our cruise control is saying, yes, this is good. Let's go, right? There's no problems here. Why is it doing that? What it's trying to do is compensate for all of that positive error that it's accumulated and remembered over time. And so what it has to do is start to get negative error, where now our set point is still 60 miles an hour, but the process variable, our speed, is at 80 miles an hour. And so what is it? Well, it's set point minus process variable. 60 minus 80 is negative 20 miles an hour of error. You see the error axis on the right-hand side of my graph there. So now we've got negative 20 miles per hour of error, and that now is adding to the error term and adding negative area to the error term, so that that error term starts to come back down. We've got to do 80 down the hill for quite a ways before, before this error term, this integral term, the integral of error starts to disappear, and we can have a reasonable controller again. So this is the problem. This is what I call the Achilles heel of the integral term, is integral windup. Anti-integral windup is a simple idea. What you do is you realize, well, the system is doing the best it can when the pedal's to the metal, whether the pedal is all the way down or all the way up. If we're going down that hill and the pedal's all the way up, and yet we're doing 80 miles an hour, well, that's just the best that the car can do, right? So anti-integral windup is this idea that we simply stop integrating, we stop adding up error if we notice that the output of the controller is 100%. If it's slammed all the way at 100% or 0%, we simply stop integrating. We stop adding up error, because obviously the system is doing the best it can to achieve our set point, and yet is not capable of doing it. So there's no point in adding up error. There's another way we could look at error, though. So far we've looked at how big the error is. That's proportional control. We've looked at how long the error has been around, and we've added it up to keep track of it. That's the integral term. But the last term, the D term, stands for derivative control. And again, don't worry too much about the math. I'm not going to make you differentiate or integrate in this class. It's more of a concept that you need to understand. But let's think about what happened to the system and the error and so forth when we started climbing the hill. You see, one of the problems is that it took a long time for the area to integrate with the integral term in order to compensate for the road slope and help us out and help us maintain the speed we wanted. How would you like it if you bought a Camaro or a brand new Corvette and you set the cruise control and you start climbing a hill, you were doing 60, you start climbing the hill and the speed drops all the way down to 50 miles an hour, and then finally 2 seconds later comes up to your 60 miles an hour. You wouldn't be happy with that at all. But that could be the kind of performance you would get without derivative control. Now, of course, you can increase the gains and do better, but derivative control is another way of looking at error. It's looking at the rate of change of error. Let's think about what happened when the car was doing 60 and it started climbing the hill. Well, what happened? Well, the speed started to decrease rapidly. Look at the curves I've got. There's just little snippets of the curves. There's the speed of the car in blue. There's the error of the speed in green at the bottom. And you notice that there's a very steep slope of both. More particularly, there's a very steep slope of the error curve. The error curve is shooting up. Now, it's not really a stretch to look at this and say, where's it going? Well, it's going to get worse, right? That's not really a stretch. That's easy to see. So what derivative control does is it looks at the rate of change of error. So not only can we look at how big error is right now, we can look at how long the error has been around and how much of it we've accumulated, or accumulated error. We can also look at how quickly the error is changing. That's another attribute or another facet of error that we could watch and hopefully perform better control. And so here's our last term. Let's look at the slope of error over time. So dE by dt simply represents the slope of the error, and all we're going to do is multiply that by its own gain, kd. So each one of these terms, the magnitude of the error, it has its own gain, kp. The integral of the error, or the accumulated error, has its own gain, ki. And then the rate of change of error, the slope of the error, has its own gain term, k sub d, or derivative gain. So with all of these things, what could we do? Well, hopefully we could not go away from our set point quite so much. The derivative control would sense, hey, we've got a very rapid rate of change of the error here. I'm going to ask to press the gas pedal because I know things are going to get worse soon, right? And in addition, the integral term then can add up error over time and realize, hey, this disturbance is not going away, so I've got to constantly push the gas pedal farther in order to maintain the set point. And of course, the proportional control term is useful in its own right, because the bigger the error, the more effort should reasonably be applied to the pedal. So this is a full PID control equation, because it looks at the amount of error, it looks at the integral of the error, and the rate of change of the error. Now, just like the other two terms, the derivative control has its own Achilles heel. It has its own problem. And the main problem with derivative control is noise in the signal. You see, when you're measuring your process variable, in our case speed, most of the time sensors are not really clean. In other words, they produce signals that vary a little bit. They have some noise in them. And the problem is that that noise can look like rapid rates of change of the error to the derivative term. So this is the problem with the derivative control term. And if you look at my error signal, say this is what we're getting from our speedometer as our the best signal we can get out of it. Well, there's rapid changes here. There's these steep slopes at the beginning, then it kind of goes horizontal, flat, and then goes to about 45 degrees, and then a steep slope, and then down, and that all happened before 1 second, right? The error is going all over the place, and it's really just noise. So noise is the Achilles heel of the derivative term. And the solution to that is a low-pass filter. It's to put a filter, electronic or mathematical, whatever, it doesn't matter. You just want to smooth out the error signal so that, and usually you smooth out the sensor signal so that the error itself is a smooth signal. And that way the slope of the error can be determined with, that's more reasonable. So this is the way that you take care of the problem with derivative control, is by a low-pass filter. Now the problem with a low-pass filter is you've got to understand the dynamics of the system and not make it cut off too much. In other words, you don't want it to... The derivative control still needs there to be some rate of change, and you need to detect it early, but a low-pass filter will increase the time required for the derivative control to do anything. On the other hand, it can help smooth things out so the derivative control does not make the control unstable. So here's our complete controller equation with Kp, Ki, and Kd plus some bias. It's the one sort of in the middle of the screen. I skipped ahead. But if you're using a Honeywell controller, then Honeywell controllers, the equation in the thought bubble up there, is a little bit different. It's the same idea, but the Honeywell control equation, which is also very common, looks different, where instead of having a gain term called a proportional gain, integral gain, and derivative gain that are all completely independent of each other, rather a Honeywell controller equation has a proportional gain that's multiplied by all of the terms, the error magnitude, the accumulated error, and the rate of change of error. But then there's a TI parameter, 1 over TI, which helps you adjust how sensitive the controller is to the integral term, or the accumulation term, and another gain, T sub D, that is multiplied by the derivative term in order to affect it. Now notice Kp, when you change it, it affects the effective magnitude of all of these terms. It changes them all. The reason for that is that often it's easier to tune the controller if the proportional gain changes all of these together. There are certain names for TI and TD. I can never remember them. TI is either reset time or reset rate. I think it's reset rate, and TD is reset time. You would think it'd be the other way around, because T sub D you'd think would be reset rate since it goes with the rate term, but that's not the case. if I remember right. I don't remember the names, it doesn't matter. The point is, there are two dominant controller equations for PID control, and you see both of them here. The so-called Honeywell in the thought bubble, and the one that I introduced to understand PID control, where we have KP, KI, and KD. Now, of course, you can go back and forth between these two. They do the same thing. There is a relationship between KI. It's simply KP over TI. And there's a relationship between KD and, of course, KP and TD, and you see it there. Now, all of the stuff you see inside of the dotted line, that's all stuff that's inside of a standard controller. You enter the set point desired into the controller, and it does the math to take in the signal from whatever sense you've got, take the difference between the set point and the process variable, and calculate the error, and then the PID calculation in either one of these forms, it doesn't really matter which one, calculates the change in the control variable, but the bias is also something that has to be entered often into the controller equation. And of course, in your cruise control in your car, the way you do that is by pressing the gas pedal to the position where you get the speed desired, and then you press go essentially on the cruise control. And so the cruise control is able to read your gas pedal and say, okay, well, we're going to adjust things from here because that's the bias position. So in summary, what we've talked about is that you have to manipulate a control variable in order to change a process variable, and that's what PID controllers do. And a PID controller will respond to error. In fact, it'll respond to many different views of the error, if you will. How big the error is, that's the proportional term. The accumulation of error, that's the integral term. And the rate of change of error, and that is the derivative term.